So we know about the energy as a quantity that a system has. It's a quantity just like momentum. There's going to be one other quantity. So there's three quantities we're interested in this course. That is the momentum that the system has, the energy that the system has, and its angular momentum. So there's a principle saying how each one of those things changes by interacting with surroundings. But, so we know how the momentum of the system changes because of an interaction. That's the momentum principle. I want to see how does the energy of a system change as a result of an interaction in a simple place, and that will tell us something about what is the form of the energy principle. What is the form of the rule that tells us how the energy in a system changes? So let me pick an origin right there. So at t is equal to 0, I've got an object of mass m that's at rest. And at time delta t, it's right here, it's gone a distance delta x, and it has a velocity I'm going to call v final. So that's the x direction. And during this time, it has got a force like so, which is just equal to F in the x direction, F times x hat. So the momentum principle will tell us everything we need to know about what the momentum is, what happened to the momentum. So m times v final, let's just look at this in the x components, m times v final is equal to the initial momentum, which is 0, plus F times delta t. So that is, I know what the final velocity is. Good. So let me just make a notation of that. The final velocity is equal to F delta t divided by m. Well, now, how far has the object gone? This is the same sort of thing where we use the momentum principle, average velocity, and position update to answer a question like, where is an object that is being interacted on by a constant force? Well, we're going to need v average, and for this case, the average is just 1/2. The initial velocity is 0, and the final velocity, like so. So that's equal to F times delta t divided by 2m. So that's the average velocity, and now I can tell you how far the object has gone. Delta x is equal to, well, it's v average times delta t. That's the position update idea. Well, v average we just figured out, so I know that F times delta t squared over 2m, that is what delta x is. And that is, so that's something we've done plenty in terms of the momentum principle, and the definition of average velocity, and the position update idea. So that is it can get to be complicated algebra. So now, for reasons of my own, I'm going to multiply both sides of this position update idea by the force itself. So I have delta x times the force which is applied. And that's equal to, well, I'm going to have to square the force. Force squared delta t divided by 2m. Now, why did I do that? That is, well, here, if you've taken physics class before, you might know something about what happens to this F times delta x. This has got a very similar structure to the delta t times F. So this is not the impulse. This is going to wind up being called the work that's being done. And now let's see what this quantity that the work is. So, and I want to do this in terms of things that I have that I can see in the final state. And the thing that I can see in the final state is the final velocity, and I have a statement for what the final velocity is. So, force times delta t divided by m is the final velocity, so let's just write this as, oh, there's a delta t squared there, I forgot to write that. So I've got F times delta t divided by m, and that's squared, but I'd have to multiply this by an m and a 2. So that's what's left behind. I multiply and divide by an m. So what I have is velocity final squared. So velocity final squared is a force times a delta t divided by an m that comes directly from the momentum principle times m over 2. So what we come up with is delta x times f, and that is the, in this case, the work from the surroundings, is equal to, and you recognize this, when v final is much, much less than the speed of light, that is the final value of the kinetic energy. In this case, the initial value of the kinetic energy was 0, so we'll just write that as delta E. And that, when properly generalized, is the energy principle. I'll state it directly. So when there is no transfer by a change in temperature, then we've got the change in the energy of the system is equal to the work that is done by the surroundings. And that is our second big principle that we're going to use a lot, the energy principle.